Hello all, I'm Drishti Jain and I'm going to be speaking about a very interesting topic. I know all of you are very excited about blockchain and to hear about blockchain with Python from me. So let's dive right into our talk. So once again, welcome to everyone. Today I'm going to be talking about blockchain breakthrough with Python. Blockchain is a buzzword going around all over. And as Python developers, aren't we all excited to get into it and explore the great world out there through blockchain that's there? Become blockchain developers, create smart contracts of our own, or maybe even create a side project which can further be used down the line. So let me tell you a little about myself. I'm a computer engineer, a tech geek, and a social entrepreneur. My nonprofit organization in India runs across 11 cities, and we impact in the sectors of environment, education, and healthcare. This is something I've been doing since a long time, and I also like to encourage a lot of students who are otherwise deprived of a good education to give them education, especially in the fields of science, maths, and English, and enable them to take up a career which could be long and fulfilling for them. I'm also an international tech speaker. I frequently share my knowledge with the tech community at various global tech conferences, and I'm a mentor to a number of students. So let's dive right into blockchain. All of us are excited about blockchain and what we can achieve through it. So the first thing about blockchain is that don't worry, considering it to be a very buzzword and maybe something that is complex outside of the regular development that all of us are used to. So imagine that two friends, friend A and friend B, have a bet between them. Or just to make things a little simple, consider that I and my friend have a bet with each other of whether we'll see a rainbow today or not. And just consider the fact that we also plan on betting 50 euros on whether or not we'll see a rainbow today. If we see a rainbow today, I say that we'll see a rainbow today. It has been raining and it has become sunny. So there's a high possibility of a rainbow to be there. And I bet 50 euros with my friend. But my friend is of the opinion that it would not be that sunny. It might rain again and we might not see a rainbow. So later on, if we have to have this as a contract, it would be very cumbersome. Consider a case that I see the rainbow, so I have won. But what if my friend doesn't follow through the verbal contract that we had and actually goes ahead and does not give me the 50 euros that we had bet upon? This is a small case scenario wherein one party could break the trust of the other party and not follow through their contract. This is a small case of two friends betting over whether they'll see the rainbow or not. And how would they decide? Because it should not be a case that I said and you said. So probably we would be looking at third-party websites, say weather.com or other weather reporting apps, if there was a rainbow spotted or not. So another party and relying on them that the information is accurate, and based on that, the outcome of our bet would take place. But imagine a real world scenario wherein there's an actual deal being made. Imagine that you went to a developer or a builder who's building buildings, a series of flats, and you want to buy that. And in that case, you would go through a legal contract, but there might be fine print. A case wherein the developer is not able to give the promised property that you plan to pay for. What happens in that case? You have to go through a long legal process, but there might be some fine print which you might not know. So the bet with a friend for a rainbow is a small use case. But if this contract were to have been on a blockchain, there would have been other people, being a decentralized network, there would have been other people who would take care and ensure that that contract is there and the party has to follow through the contract. So this is where the blockchain comes into place. Because neither just relying on the trust nor the verbal contract would make sense. And imagine a case for a blockchain. There are numerous applications of blockchain, be it from the finance industry to the real estate industry to the food industry and many more. To to understand blockchain at the core level, you can think of blockchain to be a distributed ledger technology. So just like we have ledgers, blockchain is a distributed ledger, which is online. It is not a physical entity that you can go ahead. So just like a ledger, there are records of everything, like a typical ledger, the physical ledger. In the similar way, blockchain is a virtual ledger that is there, and it is distributed across the network. Hence, it is a distributed ledger technology. Now, there are a number of key pillars of blockchain that are out there. The very first one is that it is very secure. A blockchain uses the concept of cryptographic hash that helps us to encrypt sensitive data and also ensure that the correct recipient of the information is only able to access our information. Consider a case, we have a financial blockchain wherein there are a number of transactions, and maybe you don't want your actual sum of money that you have in your account to be displayed to the world across, but maybe you're okay sharing it with your family members. So in that case, there has to be a way that only the family would be able to decrypt your information of the bank and not somebody else publicly. Blockchain is very secure, especially because it uses cryptographic hashing. There are numerous ways of hashing, and based on the blockchain, the consensus protocol, and the way the blockchain is built, different algorithms are used to make it secure. Also, blockchain is eliminates the concept of trust. It is trustless. Now, to explain it further, what does blockchain mean by when we say that it is trustless? So you don't have to put your faith on a centralized entity. It eliminates the concept of trust. Example, say that there was a bank that you had put in your money. You had trusted that the bank officials know what they're doing and they would take care of your money. But when the bank goes bankrupt, you lose your money. It might take a long legal process, maybe tens of years, to get your original money back. In that case, if this would have been a blockchain, it is a distributed responsibility. You are not trusting a central entity. So the concept of trusting a central entity and giving all the rights to that central entity get eliminated. We no longer trust a central entity. Instead, we focus on the blockchain and the distributed way of trust. It is very reliable. So the transactions that are there, they are immutable. Anything that happens once it's on the ledger, it is done. And it is possible to revoke a transaction, but it is a different process. Any transaction that is done will get recorded in the ledger. Also, multiple copies of the same data is stored across the different nodes on the blockchain. Where does this come into a very important place is consider a fact that a person places a payment for a particular product on an e-commerce platform. And then the person gets the product, but through the credit card company, the person says that I did not make this payment. So this is where it becomes difficult. The person is going to get the product for free because the credit card company would otherwise refund the amount. So all of that are the cases wherein blockchain can be used to eliminate that. Also, blockchain is very, very reliable in the sense of it is very distributed. It being centralized, it is across the globe. There's no one central geographical location wherein all nodes of the blockchain would be present. So in case we face an issue of any server being down, or if there's some downtime with the server, it would not lead to a whole blockchain going down, especially with the bigger blockchains that are there, because only a part of it would be affected. Say, if there's Ethereum, so the Ethereum blockchain is across the world, it is decentralized. If a particular part of the servers get impacted, it does not at all mean that the whole blockchain would come down to a standstill, which many a times we do see with a lot of websites that does happen, or if a bank server is down. So all of these problems which we face otherwise can be overcome when we are working along with blockchain. Now, just to give you an idea of what a blockchain looks like, just to keep things simple, because once we start from the core, it is easy to build on upon that. A blockchain is like, you can consider it to be a linked list of hashes. The first block is also called the genesis block, being the first block of the blockchain, and all other blocks are attached from it. Each block keeps knows the hash of the previous block, and it has a hash of its own, which is then kept by the next block in the blockchain. The data that you see in each of the blocks of the blockchain is the actual content that you want to store in that block. Now, this data can be series of transactions based upon what the blockchain is being intended for. For example, if we are working with data that is a lot like, for example, if you're working with data that is a lot like, say, a financial institutional data, or we are doing a lot of banking transaction through it, then that would be different. And if we are, for example, taking care that we have all of our real estate out on the blockchain, so that we are able to keep a track if the ownership has been passed on correctly. All of that can be different kinds of data based upon the application that we have. To simply put, to create a virtual image of what a blockchain looks like, it is like a linked list of different hashes, and each block has points to the previous block through, and it knows the previous hash of the previous block. Now, one important part is the digital signature, which enables the transaction encryption. If you have ever observed in your browsers, you see, especially for an HTTPS kind of a website, you see that it is secured through a digital certificate, which has a digital signature. This digital signature is very, very crucial, especially to identify if that certificate was issued correctly from the correct sender or not. And at this point, when we are talking about a distributed ledger system, that is the blockchain, a digital signature becomes very, very important. We don't want malicious attacks in our blockchain. If that happens, if that were allowed, for example, we would be modifying contents of a block. And if the other nodes are reading contents, the transactions being made at that block, then it would completely create a false blockchain. It would be transactions which are incorrect, and the validity of our blockchain would be impacted. So digital signature plays a very, very important role in doing that. Now, just to tell you, so with digital signatures, strings are generated from encrypting the transaction request with your private key. So whenever, for example, if I would also show this through an example further down the line. So there is a concept of private key and public key whenever we're talking about digital signatures. And when we use public key cryptography, both the private key as well as the public key is used. During encryption, the private key is used. During decryption through the intended party, the public key is used. Now, digital signature becomes invalid even if a single character is modified. This ensures that there's consistency as well as trust in the digital signature. And this enables authenticating the nodes across the network, and also to verify the source of any transaction, any information, any data that we are storing in our blockchain. Now, let me give you a little brief about public and private keys. Now, it is very important that your cryptocurrency wallet is secured. And there are cryptographic methods like the cryptographic hash that we talked about a little earlier. But the core concept in doing that is the cryptography that we are doing. And it boils down to private key and public key. Now, private key is the key that the owner has, and it is used to encrypt and unlock. So if I want to send a message, if I'm doing some transaction, I would encode that message. I would encrypt that message using my private key. Public key, my public key would be available to all the nodes, and they can cross-check and verify, check the legitimacy of the transaction that I have. If it actually happened by me, if it has my digital signature on it or not. And this public key will enable them to verify that this digital signature belongs to me or not. And a digital signature becomes invalid even if a single character is modified. So if somebody is almost trying to impersonate me by changing my digital signature a little, but it would make the digital signature invalid whenever other node would use my public key to decrypt the data that I've sent across the node. So the private key and the public key are very important concepts. I would encourage you to go ahead and read a little bit more about it. It is very interesting as well from the cryptography point of view, as well as the blockchain point of view. Now, let me show it through an example. Now, on the left, consider there are two people, David and Sandra. David wants to send 5 Bitcoins to Sandra. So the transaction message, the request is that like deduct 5 Bitcoins from my wallet and add 5 Bitcoins to Sandra's wallet. How would this be achieved? So David will use David's private key to encrypt this transaction request of transferring 5 Bitcoins, which would be a digitally signed transaction. The same thing we talked about, digital signatures. And it would be broadcasted to the Bitcoin network. Once it is broadcasted to the Bitcoin network, in that case, the digitally signed transaction, this request would go ahead and people would, the other nodes, that is across the Bitcoin network, would use David's public key to validate if this transaction was there or not. Once that is authenticated, the transaction would take place. Each block is a digital ledger, a sequence of transactions. Nobody is going to know exact contents of David directly, but they will have each transaction that David is performing. And that way, this would be added and the operation would be performed of transferring the Bitcoins from David's wallet to Sandra, and the ledger would be updated. And this block would be stored once everything is validated, and the blockchain would keep on moving. The blockchain would keep on building upon the next transactions that keep on coming. I hope this example especially gives you a great perspective about what it tries to happen in a blockchain at the core level. Now, this transaction was a financial transaction. It could be any other transaction as well. If I want to validate something, for example, if I'm buying organic vegetables and if I have that supply chain on the blockchain, I can also cross-check if this vegetable was actually organic or not, or what was the source of the vegetable. All of this is possible through blockchain. Now, let's talk about node agreement. So node agreement is very crucial. How do we know which transaction should be processed first? Say, continuing our previous example, if Sandra wants to spend those 5 Bitcoins, so she might be spending those 5 Bitcoins to buy a property. So these are two separate messages. One is David sending 5 Bitcoins to Sandra, and the second one is Sandra transferring those 5 Bitcoins to the real estate company. So how do the nodes among them agree which transaction comes first, which transaction comes next? This is very, very crucial, and it forms the core of how we validate that each and everything happening across the blockchain is valid and is doable. So that is wherein node agreement comes into place. It is not just secure to just have a timestamp. That is the first thing I believe most of us would have in our mind, that we can have a timestamp of each of the transactions and then just track it. But there are millions of transactions or requests that can happen at every second. So just relying on the timestamp is not the best way to ensure that we are following node agreement and all the nodes can agree at the very same time. Because an additional reason is also that the timestamp can be modified comparatively easily. If we just rely on the timestamp, then it gives a malicious attacker an entry point into our blockchain to modify the transactions. And this could have devastating effects on everything that is happening in the blockchain. So in order to do that, if a particular transaction happened before or some other transaction happen after a particular transaction, node agreement is very, very important. The node should agree upon which transaction should be given first and which transaction should follow that particular transaction. The very first one being that node agreement enables to prevent fraud. Only if we know which transaction is happening one after the other, we'll be able to prevent fraud. And preventing fraud is a key part of blockchain, which is why it is being called the future technology. The second one being networks order transactions by grouping them into blocks. So the blockchain that we saw, the data part of it is a group of transactions. So there are millions of transactions that happen in each of the blockchains. All of these transactions, which are happening at the same time, can be grouped into a block. And each of these blocks are organized into a time-related chain. That is, this block happened first, then this block. And that gives the whole system the name of blockchain. It is a chain of blocks. And we are adding that to our process, which is being called the blockchain together. Now, I've been talking a lot about cryptographic hash function, and that is what makes cryptography as well as especially blockchain to be so secure. So what exactly is cryptographic hash function? So cryptographic hash function, you can think of it as a mathematical algorithm that maps data to a bit array of a fixed size. What this also helps is if we have, say, 100 transactions that we want to hash out, or if we have 10 transactions, but we want our output size to be same because we are working on that output. So cryptographic hash function helps in doing that. Now, a core part, along with the other advantages, is data integrity. Now, consider this. Consider that there's a hashing algorithm wherein the original data has been passed through the hashing algorithm. We get a hash value, which is then passed on to the network, and that we are able to get our original data through the hashing algorithm, compare the computed hashed value, and that is what helps us identify. Now, data integrity is very crucial whenever we are working with any kind of data. Now, imagine a case you had, say, 5 Bitcoins in your wallet today. You want, and you transferred, say, 1 Bitcoin to your friend. You want your data integrity to be there. You want your wallet to be reflected as 4 Bitcoins. You don't want any malicious attack to be there. That is wherein, in the second part of the diagram, if you see, we compare the received hash value and the computed hash value. And that, comparing both of them, if they are equal, then that identifies that we have a data integrity. Also, in blockchains, everything's distributed across nodes. This enables that each of the nodes would have a copy of the data that is there. And they frequently check with each other if their block and if the blockchain that they have is valid or not. So comparing hashes enables data integrity. This also makes it almost very difficult for any outside attacker to change any part of the data, even if they're able to modify contents of a block. But since nodes are updating their blockchain with copies that other nodes have in the distributed fashion across the globe, they're able to identify that this block was tampered with and is an incorrect block, and they keep the correct latest copy of the blockchain with them. There is also an important concept of end of chain ambiguity with blockchain. So in case of blockchain, the way miners make money, they install so many servers. The main aim is to calculate the cryptographic hash function, the nonce, and identify what should be added next to the block. But there might be a case, though very rare, that two of them might calculate it together. So at that time, which block should be added and who gets that privilege of adding that block? Because getting the one who calculates it first is the one who gets that award money, which is what the miners are after, and because of which they invest so heavily on the hardware equipment that is out there. Now, the way the end of chain ambiguity is handled, so if two of them calculated together, then the blockchain waits to give the credit in the further blocks. In a blockchain, the longest valid chain is given the highest priority. So even if two of them do it together, then if they are able, in the next calculation of the block, the one who is able to do it faster gets the credit even for the previous one. That is how the end of chain ambiguity is handled in case of blockchain. Now, consensus protocol is what makes one blockchain different from the other. So the Ethereum blockchain is different than the Bitcoin blockchain. But what exactly makes it very different from each other? It is very interesting, and this is the core of why one blockchain would be able to support many things across industries, across things that can be done on the blockchain, and other blockchain might not be able to serve a particular purpose that one blockchain is serving. So firstly, consensus protocol is used for the safety of the network. Also, it allows to avoid any catastrophic system failure and discard the blocks generated by the attacker or the bad node. A bad node or the attacker, in simple terms, is tries to modify the blocks or add additional blocks in order to change the blockchain completely. That is wherein consensus protocol comes into place. Consensus in the literal sense that all nodes agree on a consensus of how to go forward, and that is the protocol that a particular blockchain would follow. Now, there are four types of consensus protocols. The very first one being proof of work. The second is the proof of stake, then proof of space, and proof of elapsed time. There are multiple more. These are the four most common ones. Let's dive into each one of them. So proof of work. Proof of work, miners compete to solve the cryptographic hash function, and proof of work is relies on compute power. So somebody who has a higher compute power is able to, by probability, is able to compute faster and gets the reward to calculate the next block that has to be added. In case of proof of stake, the miner is selected based on the higher stake. So the higher the number of tokens, any particular cryptographic currency that is associated with a particular blockchain, that whoever owns the more stake gets the first opportunity, gets the is selected to be the miner to add the next block. In proof of space, just like in case of proof of stake, it was related to the number of tokens that a person has. In case of proof of space, it incentivizes miners with the most considerable disk space, that is the storage allocated to a particular block. Proof of elapsed time was developed by Intel. So a lot of big corporations also have their own blockchains for a number of things. For example, POET, proof of elapsed time, was developed by Intel, and it is predominantly used in permission blockchain ledgers. It does not keep the identity of each of the miners to be anonymous, and it uses specialized hardware. So it has a little entry barrier to become a miner in it. But being developed by a corporation, everyone can have their own consensus protocol, their own logics to implement the blockchain. So these four are pretty widely used, and proof of work, proof of stake, you must have read about the Bitcoin blockchain or the Ethereum blockchain. So all these different consensus protocols are different for each of the blockchains. Many different blockchains also use the same one. It all depends on what the blockchain is intended to do for. Is it mainly heavily focused on financial transactions, or there are other things as well that people want to do on that particular blockchain? Now let's get into how does it actually work behind the scenes. So let me tell you the concept of nonce. Nonce, short for number ones. Now, nonce is an arbitrary number that can be used just once in a cryptographic communication for every time a nonce is calculated. And this nonce is what the miners are competing to calculate the fastest. The one who calculates it the fastest is the miner that gets selected to put in the next block. So this is very, very important. It is also called like a golden number because it is a central part of proof of work. Proof of work is the consensus protocol which enables, like, the one who has the highest compute power gets the opportunity. In case of nonce, miners compete with each other using the computing hash power. The faster they are able to compute, the faster they become the miner to add the block to the blockchain. And yeah, miners test and discard millions of nonce per second until they find the golden nonce, like the golden number, which is valid. Now, I'll also take you through an example of what exactly nonce is. To give you a general idea, the nonce is a number which, when added, gives the logic through which they can decode the hash of the previous block. Once they know that, it is able to add based on the message that is there. And once that golden nonce is found, it is added to the hashed block and the miner gets the reward. These rewards are say different amounts of the cryptography currency that the particular blockchain is using. And this is like real money in the form of cryptographic currency. And this is how the miners earn and are able to take their the invested amount that they have and earn from it. Now, for example, if there is a hash like this, originally there is a data and a nonce has to be attached to that data. And for example, SHA-256, one of the popular hashing algorithms, is used. And this is hashed out to get the hash that we want. Now, generally, in case of the Bitcoin blockchain, the hash that is there has starting zeros. So the number of zeros, if here as well you see, it is 000779. This is just an example that I've taken in to give you an understanding about nonce. So my original message was, hello all, this is Drishti Jain. It's a simple hello world message. Now, if you see the very first iteration, what in proof of work, what I'm trying to do is my nonce, the value of my number, the nonce is 0. And I added to my string, I appended to my string. So my string, instead of just hello world, this is Drishti Jain, becomes hello all, this is Drishti Jain, exclamation and 0. And the hashing of this, for example, SHA-256, of this whole string from hello to Drishti Jain exclamation 0 is the hash value that is printed. Now, I keep on trying to add different numbers to it, from 0 to 1 to 3, and I go on and on in order to find out where do I get my value of 000. And once I get that, that is the resultant nonce. And the one who finds this nonce the fastest is the one who gets the reward. And you can see that it involves a lot of computation. So the computer would calculate the nonce, check if it gives the correct hash, the number of starting zeros in the hash or not. And as soon as they get this, the hash gets appended. And that is how it keeps on going. So the one who has the highest compute power gets to actually see and become the rewarded miner. Now, let's look at the Bitcoin block hashing. Now, if you see, for creating every new hash block, there is a constant info with the version info, the previous block information with respect to the previous hash that is there. Then there's a Merkle root and the time, which is updated from time to time. Merkle root, if you're good with data structures, you must have heard about the Merkle tree. So Merkle tree is a simple mathematical way to verify data. It is a tree in which each leaf is labeled with the cryptographic hash of a data block, and every node that is not a leaf is labeled with the cryptographic hash of the child nodes. Now, with this Merkle root and the time component being updated roughly like 10 minutes every time, the other parts are the bits and the nonce. The nonce is the guessing number that we saw right now with the leading zeros of each new hash block. This also keeps on getting updated. We cannot have, say, 3 zeros to be the leading zeros in every time, like for the whole day. Then there's no point. Every miner knows it. And bits, which is the difficulty level, updated every 2016th block. After we reach that block, it keeps on updating. This whole is then applied to SHA-256, a very popular hashing algorithm, to get the new hash block. All of this is happening, and the miners are competing to calculate nonce, the very bottom part of this whole block that you see. And that is the nonce that we saw here. The nonce, like for example here, for text, my nonce was 1168. Which led to my initial 3 zeros to be there, which was my logic. So this keeps on happening in the Bitcoin block hashing function every time. Now, all of this has its core in ciphers and the way ciphers work. It is pretty interesting. If you're following along, then I would encourage you to take a paper, a pen, or a pencil and try it all along with me. Computers are able to do it very quickly. Let's see how different ciphers are actually made. We'll create our own cipher. We'll be able to encrypt our data, send to somebody, decrypt it using our key, and a little bit of maths, that's all. So the very first one is the Playfair cipher. The Playfair cipher was the first practical digraph substitution cipher. So it is called a digraph substitution cipher because we are encrypting two words at a time. It was a scheme invented in 1854, and Charles Wheatstone. It was invented in 1854 by Charles Wheatstone, but was named after Lord Playfair, who promoted the use of this cipher and encouraged the use of the cipher more. And this technique encrypts pairs of letters as a simple substitution cipher. It's a simple substitution cipher. Let's see. So taking an example of where our key is Moon Mission and our message to encrypt is greet. So the overall scenario of this would look like, for example, me and my friend want to communicate in ciphers. We don't want to just give out plain English because somebody else would be able to understand what we're trying to communicate. So the key that I share with my friend is Moon Mission. And then whatever I encrypt, I just send that message and my friend would decrypt it on their end using the key Moon Mission. In case of a Playfair cipher, a Playfair matrix is formed. And this Playfair matrix is a 5x5 matrix. If you see, we have 26 characters in our English alphabets, but this matrix being a 5x5 would only have 25 letters. So in each of the matrix, the rule is to have either the letter I or the letter J. Whichever is there, only one of it is taken. And across the 5x5, let's go row-wise. The first row, the way to go ahead with Playfair cipher is to write each letter in each of the places across the 5x5. So in case of Moon Mission, and any repeated letter does not have to be written again because we are just writing the 25 characters with either I or J. So MONIS, if you see, so a Moon Mission. So MOO has the second position, N is the next one. Then again for the mission, the M that comes has already taken place in case of Moon. So that M is already done. Then I is placed. Then S is written. And then ION again has already been done. And all the rest of the elements, if you see, have been filled through our through our alphabets. So from A to Z, all of them. Now, in order to substitute, we saw that it is a digraph substitution cipher. So GREET. And we see E is repeated. So in order to differentiate it, we add an X after the first repeated character that is there. So GRET, we'll convert it to GREXET. And in pairs, GREX and ET is how we'll encrypt our data and using our matrix. So we have divided it into GREX and ET. Now for GR, in the matrix, if you see, so G is in the second column in the third row, and R is in the third column in the fourth row. And we form a quadrilateral, four-sided figure with G and R. So we find H and Q to be there. GR are already there. So the corners of our shape that we form inside the matrix is what we take. So for GR, we take HQ. In case of E and X, if you see E and X are formed, we take C and Z. In case of ET, again, if you see E is in the last column, second row, and T is in the fourth column in the fourth row. And the when we form a sided figure through it, we find DU to be the other two elements. So the one along in the row is given the first preference. So since it is ET, so E has D in the same row and T has U in the same row. So the encrypted message becomes DU. So this is very interesting. If you were following along, this is great. So greet, a simple word, became HQCZDU. This is so different. If I'm sending this to my friend, instead of just sending the message of greet, I'm now sending this encrypted cipher, and my friend is able to decrypt it using the key Moon Mission. Another cipher is the Hill cipher. Hill cipher is a polygraphic substitution cipher and is based on linear algebra. So we earlier saw a digraph kind of a cipher. This is a polygraphic substitution cipher, and each letter is represented by a number modulo 26. Since we have 22 characters, for each of them, we start from 0 and we show it in the form of a matrix. Example, our key looks something like this, random letters. But this is a key that would be shared between the two people who are sending message to each other. And the message that we have to encrypt is ACT, the words ACT. So what we do is we write our key, we do a mod 26, and we write our key in the form of a matrix. So G, Y, B, N, Q, K, U, R, P. All of these are written as a vector. And also the message ACT is written as a vector. So A for it is we do a mod 26, so A gets 0, B gets the value 1, and so on till 25. And ACT is written as 0 to 9, and then we do a multiplication, and again a mod 26 till we find the actual characters that are there. So the value ACT that we saw turned into POH, and this can again be decrypted in the similar way using our key. Isn't it interesting how ciphers work and how it is impacting blockchain now? Now, we have been talking about miners. So what do miners do? Miners mine, right? Is this the mining? No, this is not the mine that I'm talking about. This is how the blockchain mining looks like. This is the way we mine minerals from our ores in the Earth's crust. But when we talk about mining in the blockchain, this is how it looks like. And this is the mining that I'm talking about. A pool of computers, there are mining pools, a pool of nodes come together as mining pools, different computers with high compute powers if they are in a blockchain of proof of work, or if it is about proof of space. In that case, it is about the disk space that is there. And this is how mining looks like. In minings, in case of mining pools, nodes span together in groups and divide and conquer the task. For example, calculating the nonce. Imagine that the value of the nonce is, say, 10,000. So if there are multiple nodes in the pool of a particular mining pool, they would probably divide the task. Instead of going from 1 to 10,000, if there are 2 of them, they just divide and conquer the task. So from 1 to 5,000 is what one node would take in, and from 5,001 to 10,000 is what the other node would take in. This would reduce the time in which they have to find out the answer, the nonce value. And they do a pooling of resources by miners, and this split the reward based on the work and contribution to the probability of finding a block. So a simple way of finding of how each of this is working and how we can go ahead with it through mining pools, because there might be a node in the pool who is not contributing that much in terms of compute power, but is still contributing and has a share. Say one node has a 20% share in contributing and the other has 80%. So when they get the reward, they would split it 80-20 again. Now let's build a blockchain with Python. So this is the blockchain. Out of the wonderful concepts that I saw, that I shared with everybody, coming back to building a blockchain in Python. So a blockchain, as you know, is a sequence of blocks. You can think of it as linked lists of hashes. Each of it has a data, a hash, and a previous value. Now, if you see, the first block does not have a previous hash because it is the genesis block, the very first block of a blockchain. That was the whole blockchain. Each block in a blockchain has a message, a hash, and a previous hash. These are the most important things that have to be there in a blockchain for sure. The message is dependent upon the application that you're doing. Do you have financial transaction data? What kind of transactions are you storing in your digital distributed ledger? The hash is of the current block, and the previous hash, so that we are able to firstly validate if this block is valid, if it knows the right previous hash, and also to create the link of blocks to create the blockchain. Now, each of the blocks, to simulate the same in Python, each of the blocks has a hash, a message, a previous hash, and we are chaining it in the form of a blockchain. This is the code of creating your own block for the blockchain. And then once you append all of these blocks together, you will be able to create a blockchain. Now, on the back end, I created a basic blockchain wherein I have data based on transactions that are being made by a particular big oil company. So there were transactions made on metals and minerals, transactions made on fuel and metals, and each of this is calculated. If you see the first one is the Genesis block, you see there's no previous hash because it's the Genesis block and the hash value. And the next block has the previous hash value. It has its own nonce. The nonce, the message that I'm trying to store in my blockchain is transactions on metals and minerals. So this, when passed through the SHA-256, in order to do this, the nonce is 1413. That is wherein I get this value. And similarly in the next one. And I'm also checking if this is a valid blockchain or not. To check if it is a valid blockchain or not, the previous hashes can be compared, if it is pointing to the correct hash or not, and if the encryption has been done correctly. So this is how a blockchain looks like. And now there are different things. You can work on transactions on metals and minerals, of transactions on fuel and metals. It is up to you. What do you want to do with your own blockchain? So go ahead and explore as much as you want to. To show you how blockchain technology looks like, now in our previous example, we were encrypting messages, like a high overview of what the company has done and what that block has the different messages for. Otherwise, each block would have like a header. The header would contain the hash part, like the hash and the previous hash of our code. All of that is together. And if you see, there are different transactions in the first block. All of this create the hash of the first block transactions, which is stored. And this hash is also kept by the second block. And what this helps in is to keep it in a sequence. We get to validate if it is a correct block being stored. And this is then circulated as a copy to every other node in our network. So creating it through our code, if I have my data something like this, I'm calculating the hash. I'm also printing out the nonce that created like 3 starting zeros for my hash. And there are different transactions that are there. Now, one transaction happens after the other transaction, and there can be a correlation into this, which is being handled by another factor. So this is how a blockchain transaction would look like. Now, a great place to start, especially if you're somebody who's new to blockchain and you're all geared up and fueled up after my talk, is the Bitcoin white paper. It has been written pretty very well. It is great to understand the core concept of blockchain. Why did people think about it, and the logics behind creating the Bitcoin blockchain. So the Bitcoin white paper is a great place to start off to see where all of this can be applied to. Now, coming to different Bitcoin applications, we talked about a lot of different applications of where each of the concepts helps and gives the advantage to blockchain. Let's look at an overview of the different applications of blockchain that are there. The first one being land disputes. So there are many cases wherein it is possible that you buy a property instead of from directly the government, you're buying it from an existing owner. How do you know if that owner actually owns it, or they do not own it, but they have some false papers and you tend to buy it? And when you realize these are false papers, your money is gone. You don't have the property. You are at a big loss. This can be completely avoided through blockchain. A great example is that whenever there's a new land that the government is selling, the government can put it on their blockchain, which can validate that the government sold it to person A. And then when that person A sells it to person B, the same would also be stored on the blockchain. So whenever a person C comes to buy from B, they can validate through the blockchain that this was originally sold by the government to person A. Then in this particular year, it was sold to person B. And now I'm buying it from B. So B is the legitimate owner of the property and I can buy it from that person. It would be a legitimate deal and I would be able to get it. This would avoid land disputes, which are a big issue across the world. The other one is the medical record management. Now, medical records are very sensitive information. There's also a lot of data that is useful and it can help a lot of people, especially with the global movement. If medical data is present on a blockchain and people have the right authority access to it, hospitals and medical institutions, and if due to some reason, somebody meets with an accident in a country that they currently do not reside in. And if the medical records have been on the blockchain, it will be easy to identify if there are any allergies, if a person is allergic to a particular medicine, so that the doctors in the new country can take care according to the record that is there. There's also a prototype called MedRec, which is supported by the MIT Media Lab in the US, which applies blockchain smart contracts to create decentralized content managing system for the healthcare industry. So this is not just an application, or all these things that I'm sharing are not just applications being thought of. This medical record management is actually being implemented in real life in the world. So it is great to see the great things that can be achieved through blockchain. Another great example is food safety. So imagine you're buying an organically grown lettuce, and there's a normal lettuce. Generally, there's a price difference, and the organically grown is priced higher. But how do you ensure that the company selling it is not just repackaging normal lettuce with the original lettuce pack? How do you validate it for you as a consumer yourself? You don't want to get into a big hassle, but you want to know if what you're consuming is the right thing or not. In that case, if the product supply chain was on the blockchain, you would be able to validate, go on the blockchain and see where your lettuce came from. If it was from a farm which follows organic practices, or was it a farm which does not follow organic practices, and you can achieve that. Another great application being done in the world is for gem tracking. If you want to buy gems that are ethically sourced and you want to validate that, so blockchain is a great way to do that. And it's being used by a lot of big players in the industry. And because consumers want to know where the products that they're buying from come from, because they are paying a premium on the price to have it ethically sourced, to have it to grow vegetables sustainably. So all of that is actually the right, and blockchain achieves a consumer to exercise that right very, very easily. Also, art acquisition and ownership. There are so many duplicates or so many forgery that can be done for art. How does a person come to know if it is an authentic art piece by the correct artist or not? In that case, a blockchain plays a key role. The art can be known who created it, and if it has been passed on across the owners, similar to what I talked about during the real estate case, the art ownership world is also adapting blockchain, because it is a great way to ensure the authenticity and prove the ownership of that art with the person. So yeah, that's all from my side. I know after my talk, you must be very excited to try out blockchain, try out the codes I shared to try blockchain in Python. And also the Bitcoin white paper is a great way to start. You can connect with me over social media, follow me across these platforms. And yeah, it was great to speak at the PyCon Poland conference. And yeah, joining in as a speaker. Thank you so much. Have a great conference ahead.